Yeah, so this is an interesting point. I mean, simplicial complexes, abstract simplicial complexes, where we have this characterization without requiring every point to have like a location in space, for example. Um, Compared to like an embedded simplicial complex where we might have that or them in space. If we consider like abstract simplicial complexes, um, those you could think of these, and this is actually quite important at a practical level for our work. You can think of them as what is called a combinatorial description of the space of a topological space. What I mean by combinatorial is it's built up out of pieces that are glued together. And guess what? The gluing involves colimits. You can stick these things together. In other words, push outs. You can kind of stick them together, right? Glue them together. So, like if I wanted to glue one simplicial complex here from by one from B to C, um, and with some other D here, and I want to glue these together, I could take the push out along this edge, right? So I take the push out. So in other words, I identify. It's like I don't. So a coproduct would mean I put these next to each other, or a coproduct would just be like putting them next to each other. Um, a push out or colimit in general will be like I take these and I stick them together. I glue them together. So I glue around C. So these are considered the same point. I glue around B. Those are considered the same point. But more than that, importantly, this edge is considered that edge. Mm-hmm. Like you could have this be a different edge, in which case we'll go like that. But I'm saying that if you wanted this to abut this sort of, if this is the same edge, not just the same 2 points, but the same edge, you would also do a push out around this edge. You do a colimit around, so glue those together. Again, it's like sticking a tinker toy together. And then you have this right next to this, right? And then you have essentially, I'll draw it here, but A, C, B. And then maybe D like that. But maybe this higher dimensional thing is in here, but these are just pairwise connection here with D. And these are just pairwise connection. This is and so we don't have to draw this in. And so my point is, this is combinatorial structure. This can be built up out of pieces that we stick together. And that's very important at a practical level of like computer, the computer description of it. So this is kind of a digital way of representing it that we can build up. And we can use things like the Vietoris-Rips complex. So with a given a set of points, we can form an abstract simplicial concept and complex out of it by building it up out of these pieces for these points that lie within a certain distance of each other. These cleats lie within a certain distance of each other, maybe pairwise, maybe all together, and then we can build it up. And in fact, not to tip my hand too early, but you can do this in CATLAB. You can build up these structures. It's actually rather pleasing. You can stick these together. And in fact, the definition of these structures is as a C set. These are C sets. These are defined based on a variant of what are called simplicial sets, delta sets. So you can build these up in CATLAB and assemble these together. And ask for critically this face relation. This is the notion of a face relation, right? We can go from, so I want to draw your attention to this. You remember earlier we were talking about like this notion of a face relation. If we have L, we can go to its vertices, or remember if we had a category here, edge, source, target, and we have V. This is kind of Getty gets boundaries. Remember that? Or spaces, you could call them. This is kind of Getty gets boundaries, right? You go from this to get its boundaries, the edges. You go from them to get their boundaries, A and B, B and C, C, A and C. The boundaries of each one. You could go from this guy to get its pairwise boundaries, this guy. So in CATLAB, you can do that. There are these nice things to map down in a dimension, map down in a dimension, map down. And this can be at the heart of describing topologies for many sheaf problems. So it's going to be like we start with this, we go down a level to its edges, we go down from that to its vertices. Maybe we have data about on the vertices, we have some data at the level of the whole complex, and we have some data at the level of edges. So maybe we have data for all three age groups together, and then we have some data maybe every year, and we have some data every month from these two, this two, maybe data every week, or probably more likely this will be more frequent, the coarser one. This will be so more frequent, coarser, less frequent, pairwise, and then less frequent overall for particular age groups. Maybe that's once a year. Yeah. Very, very handy.